Welcome to the last Engineers Newsletter live broadcast of 2008. Today we'll be covering the potential conflicts that could arise between ASHRAE Standard 62.1, 90.1, and VAV systems. I'm Jeannie Harshaw from Trane's Applications Engineering Department, and I'll be your host for today's broadcast. Through our association with the American Institute of Architects, credit towards continuing education can be earned for viewing today's broadcast. If you are an AIA member, make sure you provide your member number to your local host before leaving today's session. In several states, this certification can also be applied to engineers' continuing education requirements. So please check your state's rules to see if this might be applicable. Today, designers often must comply with the requirements of two key ASHRAE standards: Standard 62.1, 2007, Ventilation for Acceptable Indoor Air Quality, and Standard 90.1, Energy Standard for Buildings except Low-Rise Residential Buildings, for two important reasons. One, they've been incorporated into many building codes, and two, requirements from both are prerequisites for LEED NC certification. It's not surprising that the ventilation requirements of 62.1 and the energy limiting requirements of 90.1 could be viewed as conflicting. The more outdoor air introduced for ventilation, the greater the need to condition and dehumidify. In other words, more energy is needed. Our goal today is to cover the three areas that pose the greatest potential for conflict in VAV systems: demand-controlled ventilation, dehumidification, and simultaneous heating and cooling, and to provide design engineers with strategies to comply with both standards in these areas. At the end of the broadcast, we'll have a question and answer session, so please fax in your questions during the broadcast to the number on your screen. To cover this information today, we have three presenters. Dennis Stanke, a Trane Staff Applications Engineer and ASHRAE Fellow, is currently Chairman for SSPC 62.1, the ASHRAE committee responsible for Standard 62.1. Dennis also serves on the USGBC LEED Technical Advisory Group for Indoor Environmental Quality, the LEED EQ tag. However, his primary role is to help customers with the design and application of HVAC systems in buildings. Joining Dennis is Mick Schwedler. Mick is Chair of SSPC 90.1, which was responsible for writing ASHRAE 90.1 2007. He has also contributed to the ASHRAE Green Guide and is a member of the LEED Energy and Atmosphere tag. And like Dennis, Mick's primary role is also helping designers properly apply Trane products and systems. And we are also very fortunate to have Steve Taylor of Taylor Engineering. Steve is also an ASHRAE Fellow and one of the primary authors of the HVAC sections of ASHRAE Standard 90.1 and California's Title 24 Energy Standards and Ventilation Standards. In previous years, Steve served as Chair of Standard 62 and was a member of the 90.1 committee. He currently also serves on the LEED EQ tag. As you will hear, these three are very well versed in ASHRAE Standard 62.1 and 90.1. And we have a lot of information to cover. So Dennis, would you get us started with the 62.1 requirements?
Standard 62.1 includes many requirements related to proper ventilation. Standard 90.1 covers energy-related requirements. Among all the requirements in both standards, a few may seem to conflict. The three areas mentioned most relate to part load ventilation control, dehumidification, and minimum primary airflow settings on VAV boxes. We start with ventilation control, which Standard 62 calls dynamic reset. It takes energy to cool and dehumidify or heat outdoor air that's introduced into the building, so it's important to control it and avoid overventilation. In many buildings, the outdoor airflow needed at design conditions is quite high, but it drops off significantly at part load. Since energy can be saved by reducing outdoor airflow to match the current demand, Section 627 of Standard 62 allows dynamic reset. Optional controls can be used to reset either the outdoor air intake or the zone airflow, or both. These controls respond to changing conditions such as variations in zone occupancy, system efficiency, or outdoor air intake during economizer operation. We'll talk about the first two of these, starting with variations in zone occupancy. Actual population changes the demand for ventilation, so control approaches that adjust zone outdoor airflow in response to current population are often called demand-controlled ventilation. But before we discuss operating options further, let's look at design requirements. For design purposes, we need to determine how much outdoor air is needed for each zone. These calculations are straightforward. First, look up the prescribed rate per person and the rate per square foot in Table 6-1. Then multiply by zone population and floor area respectively. Add these two together to find the minimum outdoor airflow required in the breathing zone. Then look up the default value for air distribution effectiveness in Table 6-2 to correct for any short-circuiting due to diffuser placement and supply air temperature. Finally, find the minimum outdoor airflow for the zone. This is the design value, but zones usually operate at less than peak population, so the actual outdoor airflow needed during operation can be reduced. The current zone population can be established using a variety of approaches. ASHRAE 62 lists some examples. Population can be estimated using a time-of-day schedule. This estimate might be fairly accurate in school classrooms if schedules and class sizes are predictable, but it's probably not very accurate in fast food restaurants or office conference rooms. Binary occupancy sensors can be used to register either design or zero population. They can be used in any zone, but are probably best suited to small conference rooms, private offices, museum display rooms, and so on. And it's possible to actually count people in some zones based on ticket sales in movie theaters, for example. However it's determined, the ventilation system controller uses the current zone population to solve equation 6-1 for the zone outdoor airflow currently required. Then the controller can take appropriate action, which usually means opening or closing the outdoor air damper. But as an alternative to estimating population, many designers want to use CO2 sensors to reset zone outdoor airflow. This approach works because, as the steady-state equation shows, the current per-person outdoor airflow rate in a zone is inversely proportional to the difference between indoor and outdoor CO2 level. Therefore, differential CO2 can be sensed, and a controller can adjust zone outdoor airflow or damper position to change the effective ventilation rate per person. This approach has been widely used in the past and will probably continue to be popular. So if a designer wants to use zone-level demand-controlled ventilation to respond to variations in population, Standard 62 allows it. We covered this topic in a 2005 broadcast, as well as a newsletter and a couple of journal articles if you want more details. But what about dynamic reset based on variations in efficiency? As zone airflow changes in response to changing thermal loads, the system ventilation efficiency also changes. So the actual outdoor air needed at the intake is different at part load than at full load. Standard 62 recognizes this and allows optional controls that adjust outdoor air intake flow in response to variations in system ventilation efficiency. We refer to this approach as ventilation reset control. Before I explain this in more detail, let's talk about efficiency. Remember, in a multiple zone recirculating system, one air handler supplies a mixture of outdoor air and recirculated air to more than one ventilation zone. The outdoor air needed at the intake depends on the outdoor air required in all zones and how efficiently the system delivers it. One zone, the critical zone, determines the outdoor air fraction required in the primary air. All non-critical zones receive the same fraction of outdoor air, even though they don't need this much. So the critical zone is ventilated properly, but all other zones are overventilated. This means that some unused outdoor air recirculates, but some leaves the building. So system ventilation efficiency is less than 100%. Standard 62 recognizes this characteristic of multiple zone systems and requires designers to account for it. As these multiple zone equations show, the intake airflow at the air handler depends on the outdoor air needed in all breathing zones and the system ventilation efficiency, which according to Appendix A depends on the system primary airflow and the current discharge airflow to the critical zone. In VAV systems, both zone and central fan primary airflow change at part load. So even with constant population, these airflow changes result in variations in efficiency and required intake airflow. With this in mind, one way to dynamically reset outdoor airflow in VAV systems with DDC controls is to respond to ongoing efficiency changes. This is what ventilation reset control does. Using current information collected from the VAV boxes, the building automation system finds the current outdoor air intake flow required. Here's how it works. Given breathing zone outdoor airflow and zone air distribution effectiveness for each zone, the minimum zone outdoor airflow required can be calculated. Primary airflow, which is the same as discharge airflow in single-path VAV systems, is measured continuously at each VAV box. Using these values, the current discharge outdoor air fraction can be calculated. Every minute, the building automation system collects all of this information from each zone. It adds up the breathing zone airflow and the discharge airflow for the zones, then calculates the average outdoor air fraction for the system. This value, along with the critical zone outdoor air fraction, is used to find the zone ventilation efficiency. Then, using the lowest of these as a system ventilation efficiency, the current outdoor air intake flow needed can be found. By introducing outdoor air at this rate, the critical zone is properly ventilated, and of course, all other zones receive excess outdoor air. Let's look quickly at an example. Here's a single-path VAV system with 6 zones. At 100% load, we solve the multiple zone system equations to find the highest intake airflow needed, 8,800 CFM. I don't want to go through all these calculation details today. We've done that before in broadcasts and in newsletters listed in our bibliography. But notice that at 100% load, discharge airflow in some zones is at the design value, but it's lower in other zones because of load diversity. If we don't use ventilation reset control, the system needs design outdoor air at all loads. But as you can see, by solving the equations again at the 90% load condition shown, the system only needs 8,400 CFM for proper ventilation. System ventilation efficiency goes up because less unused outdoor air leaves the building in the exhaust air. Conservatively designed multiple zone systems always need less than design outdoor air at part load. This is why ventilation reset control is one good way to dynamically reset intake airflow and save energy. Demand-controlled ventilation applies to occupied zones, while ventilation reset control applies to multiple zone systems. Standard 62 allows designers to combine these two dynamic reset approaches. Zones can use demand-controlled ventilation to adjust for population changes, and the system can use ventilation reset control to adjust for efficiency variations due to changes in airflow. Trane calls this combined approach ventilation optimization. Let's look again at our 6-zone system, this time using a CO2 sensor in one zone and a time-of-day schedule in another zone. We see that at design, nothing changes, but at part load, a CO2 controller determines the required outdoor airflow in one zone, and a time clock determines the effective population to find the required outdoor airflow in another zone. Using these lower than design airflows, we use the multiple zone equations and find the current required intake airflow. But after doing the calculations, we find that at this example load condition, the system only needs 7,200 CFM of outdoor air, which is significantly less than the 8,800 CFM needed at design. So in summary, Standard 62 allows optional dynamic reset, including zone-level demand-controlled ventilation, system-level ventilation reset control, or both. And what does Standard 90.1 require, Mick?
Well, The intent of demand-controlled ventilation is to reduce the amount of outdoor air brought into the system, which in turn reduces the need to condition that outdoor air. On a hot, humid day, we still need to cool and dehumidify the outdoor air, but not as much of it. The same thing occurs on a cold January day here in La Crosse. The less outdoor air we bring in, the less energy needed to heat that air. The concept has been described on a number of broadcasts where we discussed the use of different sensing devices. In this example, carbon dioxide sensors are installed only in those zones that are densely occupied and experience widely varying population. Zones that are less densely occupied or have a population that varies only a little are probably better suited for occupancy sensors. Finally, zones that are sparsely occupied or have predictable occupancy patterns may be best controlled using a time-of-day schedule in the building automation system. Any of these methods can be used. While demand-controlled ventilation saves energy, it isn't always required by Standard 90.1, which defines the minimum requirements for an energy-efficient building. But there are some specific systems for which 90.1 requires demand-controlled ventilation. Let's look at them. Section 6439 of 90.1 2007 is titled Ventilation Controls for High Occupancy Areas and is mandatory. It specifically describes when DCV controls are required. The text of the standard is shown on the slide. When a space is larger than 500 square feet and has a design occupancy of greater than 40 people per 1,000 square feet, that's 25 square feet per person, then we have to examine the system. If the system has one or more of these, an air side economizer, or an automatic modulating outdoor air damper, or a design outdoor airflow greater than 3,000 CFM, then that space is required to have demand control ventilation. This was determined to be a viable system size for which the energy savings were significant enough to warrant requiring the additional sensors and control systems to reduce ventilation airflow when the space is partially occupied or not occupied at all. There are also cases when it does not make sense to require DCV, so there are exceptions. Ventilation controls would not be required in these areas. If the system has an exhaust energy recovery system as described in a prescriptive section of the standard, or if there is not communication between direct digital controls at the zones and the central control system, or if the system outdoor airflow is less than 1,200 CFM. Note that this is system, not zone airflow. Now that we know what the standard says, let's try to figure out when it might apply. Putting my engineering hat on, the high occupancy spaces that come to mind are assembly, whether it be places of worship or an auditorium. Also spaces such as lecture halls, lobby areas, and cafeterias may meet the criterion of a high occupancy space. Then the most likely of the three other requirements are that either the system has a required ventilation rate over 3,000 CFM or an air side economizer. Note that if the system ventilation is below 3,000 CFM, DCV may still be required. There are a lot of systems with air side economizers. If the zone meets the area and density thresholds and there's an air side economizer, then demand control ventilation is required. Finally, even if the zone has characteristics for which DCV would be required, it is exempt if the system outdoor air quantity is less than 1,200 CFM. Let's look at the 90.1 economizer requirements, which we covered in depth in a 2006 broadcast. The locations and system sizes in which an economizer is required are shown here. The drier or cooler the climate, the smaller system size for which economizers are required. For example, in Denver, economizers are required on systems of just over 5 tons, and in Chicago, just over 11 tons. There are a number of exceptions, but due to time available, we won't cover them today. Using that information, we can see that the southeastern U.S. is the only portion of our country for which economizers are not required for any system size. If a project is in the northern or western U.S. or Canada, there are many systems on which economizers are required. A question many people ask is, does this requirement apply to a classroom? In this case, we'll look at a middle school classroom. ASHRAE 62.1 gives default values for the number of people per 1,000 square feet. These are only to be used if you don't know the occupancy of a particular space. In the case of a middle school classroom, the default is 35 people per 1,000 square feet. This is lower than 40 people per 1,000 square feet, so this is not considered a high occupancy area. Dennis has put other examples into the written newsletter. Okay, Steve, Dennis and I have gone through the requirements of the two standards. Some people see conflict. What do you think?
They are often perceived as being in conflict, but are they? I don't believe that there are any conflicts in theory. While Standard 90.1 requires demand control ventilation for certain applications, Standard 62.1 allows DCV and other dynamic reset strategies to be used in any application. So no conflict exists. It's possible to meet both standards at the same time with a single design, at least in theory. In practice, demonstrating compliance with both standards is made difficult by the lack of specific details in both standards. How do you design and control DCV systems so that compliance with both standards is assured? In neither standard is the design of DCV systems well defined. Here's the definition of DCV in Standard 90.1. DCV is a ventilation system capability that provides for the automatic reduction of outdoor air intake below design rates when the actual occupancy of spaces served by the system is less than design occupancy. This definition is clear as to intent: reduce outdoor air rates when occupancy is below design levels, but is lacking in details. What kind of devices can be used? The 90.1 User's Manual focuses on the use of carbon dioxide sensors, probably because that is the most common approach historically. But the definition is certainly general enough that many other technologies could be used, including those mentioned in Standard 62.1, which I'll discuss next. Standard 62.1 is also very general. In fact, it's even more general. As Dennis pointed out, Standard 62.1 allows dynamic reduction of outdoor air rates not only when occupancy is below design, but also if any design condition used to determine the outdoor air rate changes. Dennis discussed various control options that designers might use, but the most common dynamic reset approach is demand control ventilation, and is the first application example listed in section 6.2.7, although the term demand control ventilation is not used. Several examples of DCV are listed, such as scheduling ventilation based on expected occupancy schedules, using people counting devices such as turnstiles, and using CO2 concentration. Not listed but clearly an option are occupancy sensors. From a practical standpoint, I would argue that occupancy schedules and occupancy sensors could be used only to enable the full design outdoor air rate when people are scheduled or sensed to be present, and allow ventilation to be shut off when people are not present. These two measures could not allow a partial reduction in ventilation rate because only the presence of people is known, not the number of people. To partially reduce outdoor air rates during occupied periods, either a people counting device must be used, although certainly that's not a common approach, or CO2 concentration must be used. I'm going to focus on CO2-based demand control ventilation since it is the most common approach. The theory behind using CO2 concentration to control ventilation is described in detail in Appendix A of Standard 62.1 User's Manual for single-zone systems, such as that shown in this schematic. Outdoor air is introduced at the air handling unit, optionally mixed with return air, then supplied to the space. Some of the supply air short circuits to the return if the zone ventilation effectiveness is less than 1, and the rest mixes with the room air. Some room air exfiltrates from the space, while the rest is returned to the air handler. Using basic principles, an equation is developed that correlates differential CO2 concentration, that's the difference between the indoor and outdoor concentrations, to the outdoor air ventilation rate. I'll discuss the equation in more detail later. The derivation of the CO2 ventilation rate equation includes two key assumptions. First, it assumes that CO2 is generated at a rate proportional to the rate that odorous bioeffluents are generated. These bioeffluents are what we are trying to dilute. They are the fundamental reason why Standard 62 includes an occupant component to the space ventilation rate. The second assumption is that CO2 and bioeffluents are generated at a rate proportional to activity level in a known manner, and that activity level can be reasonably predicted for a space in question. While there is research that supports both of these assumptions, there is nevertheless some uncertainty. I will discuss later a new research project currently being developed by ASHRAE that will be looking into this issue further. Here is the CO2 equation once again. Dennis discussed most of the variables. Two parts of the equation which Dennis did not discuss are M and the constant 8400. M is the activity level of the occupants and expressed in a unit called MET. And 8400 correlates CO2 concentration rate with the MET level. The room air concentration is measured with a CO2 sensor, which I'll discuss shortly. CO2 in the outdoor air can be measured, but in most locations, the concentration can be conservatively estimated to avoid the additional sensor. This actually can reduce error in underventilation because it avoids the compounding error of the additional sensor. As we will see, CO2 sensors are not perfect. A typical assumption is 400 ppm. This is conservative because in very few locations will the ambient concentration be less. In cities where a lot of combustion takes place, this assumption may be too conservative, and some energy-saving potential may be lost. An outdoor air CO2 sensor might be a good investment in those cases. This table shows the maximum CO2 concentration that can be expected in example spaces given the activity level listed, using the default occupancy density suggested in Standard 62.1 and assuming 400 ppm outdoors. Other than offices, they are higher than 1,000 ppm that is often used as the set point for DCV under 2001 and earlier versions of Standard 62.1. This is because the CFM per person is lower under the current standard. So under the current standard, it's okay to have a reading above 1,000 ppm. Let's get into the details. The user's manual outlines a step-by-step procedure for CO2-based DCV. First, calculate the design outdoor air rate, assuming all occupants are present, per the standard 62.1 equations that Dennis discussed. Next, use the same equation, but assume 0 occupants. Call this value VAT, or the total ventilation rate based on the area component only. Then, calculate the steady-state CO2 concentration using the equation on the previous slide. Call this value CO2 max. These values are used to configure the space CO2 sensor, or a CO2 sensor paired with a signal converter or proportional relay, which must be able to provide a signal proportional to CO2 concentration over an adjustable range. For instance, the sensor would be adjusted to provide a 20 milliamp signal at CO2 max and proportionally down to a 4 milliamp signal at the ambient concentration used in the calculation of CO2 max. Almost all commercial CO2 sensors have this capability without the need for a converter or relay. The final step is made in the field in conjunction with the air balancer. The damper actuator or linkage would be adjusted so that at the maximum CO2 sensor output, such as 20 milliamps, the system would deliver the design outdoor air rate, VOT. At the minimum signal, 4 milliamps, the damper position is adjusted to provide VAT. Many people thought that the addition of the area-based building component to the ventilation rate equation in 2002 would make CO2 DCV much more complex. In fact, as the above procedure demonstrates, it is actually simpler. Under the 2001 and prior standards, a controller would also have been provided, which introduces the complexity and the instabilities of control loops and control logic. Control loops are not required under the current standard. Here's an example showing how this DCV logic would perform. The lower line is the minimum breathing zone outdoor air rate required by Standard 62. The next line is the rate that the proposed control logic would provide. The upper line is the space CO2 concentration. Note that except at the point where no occupants are present, and at the point where the peak number of occupants are present, the DCV control logic will provide higher outdoor air rates than the minimum required. So the proposed DCV logic is simple, but it is a bit conservative. But I think that is a small price to pay for simplicity.
Excuse me, Steve. I just want to interject. 2 slides back, you showed steady state CO2 concentrations for different example occupancies, and some of them got pretty high. Those are absolute levels expected indoors. But on the last slide, you showed a plot of population versus differential CO2 level. I just want everybody to be clear that if you had used absolute levels on that plot, the highest CO2 level at design would have been about 1650 parts per million rather than 1250 parts per million. Okay, sorry.
Thanks, Dennis. So CO2-based DCV requires the use of at least one CO2 sensor located in the space. There are 2 common sensor technologies, solid state and infrared. Infrared is by far the most common because it is less expensive and also is relatively rugged. The solid state sensor can be damaged if exposed to concentrated organic compounds such as wall paint. There are 3 commonly used infrared sensors: single beam dual wavelength, and dual beam single wavelength. The single beam sensors are of course less expensive, but more likely to get out of calibration. To keep reasonably calibrated, most use a self-calibration technique that assumes that the space will be unoccupied at night and thus self-adjusts its reading to approach 400 ppm. This logic, of course, will not work if the space is always occupied, like an airport, and if the nighttime infiltration or ventilation is not sufficient to bring the room concentration down to ambient. The dual beam design, shown here, and dual wavelength design are intended to improve long-term calibration, guaranteed by most manufacturers for 5 years or more. The accuracy and stability of all 3 types of sensors are being tested at the National Building Controls Information Program at Iowa Energy Center. The NBCIP research project will be evaluating almost all of the currently available commercial CO2 sensors, both for initial accuracy, as shown in this graph, and for long-term accuracy. The project should be completed and published late this year. The published research will include brand names, so it will be particularly useful for designers. Neither Standard 62.1 nor Standard 90.1 get into details about how accurate CO2 sensors must be. I expect Standard 62.1 may be changed to address CO2 DCV issues like this in the future. Accuracy is addressed in California's ventilation standard. It requires 75 ppm accuracy at 1,600 ppm of CO2. It is clear from this slide that a few of the sensors being tested by NBCIP do not meet this requirement. California also requires that sensors not require calibration for 5 years. Only a few sensors currently on the market will make that guarantee, including most of the dual beam sensors. Here's an example of the hardware required for a single zone system. First, we have the CO2 sensor located in the space, and I mean in the space, not in the return grill and not in the return duct or in the air handler. The reason for this limitation is that we are trying to measure the air quality in the breathing zone. And with many systems, return air CO2 will be diluted by short-circuiting supply air at the ceiling or by outdoor air leaking into the return ducts or plenums. Next, we have the signal converter or relay, if one is required to convert the signal from the sensor to the signal expected by the return air and outdoor air damper actuators. If the damper actuators accept a standard 40-20 milliamp signal, no converter is generally needed, since most commercial CO2 sensors can be adjusted to provide a 4 to 20 milliamp signal proportional to CO2 concentration over an adjustable range. The last step is the test and balance step, where the sensor output is adjusted for the proper CO2 range and the damper actuators or linkages are adjusted to provide the full occupancy and no occupancy outdoor air rates. So DCV is simple with single zone systems. How about multiple zone systems like VAV systems? Unfortunately, the math is a bit complex with multiple zone systems, so no one has developed an exact technique that is proven to theoretically meet Standard 62.1 under varying operating conditions in all zones, both densely occupied spaces with CO2 sensors and sparsely occupied spaces without CO2 sensors. Fortunately, ASHRAE has initiated a research project to investigate this and other DCV issues. Unfortunately, the project will not be complete for a couple of years. In addition to making sure that the control logic meets Standard 62.1, we also want it to be efficient to meet the intent of the DCV requirement in 90.1. The exact means to do that are not self-apparent, however. What exactly do you do when the space CO2 starts to rise? One option is to increase the zone minimum airflow rate, but this may increase simultaneous heating and cooling at the zone, mixing of hot and cold air in this dual fan, dual duct example. Or we could increase the outdoor air minimum position, but this will increase outdoor air to all zones, not just this zone. If the outdoor air temperature is below the supply air temperature set point, this can increase heating energy. And if the outdoor air temperature is above the supply air temperature set point, this will increase cooling energy. So, which is the most energy efficient? We don't know yet exactly. That is part of the ASHRAE research project. But here's one approach that we do in our office. Based on limited modeling, we feel this logic will be optimum when the system has an outdoor air economizer. The logic is to take the CO2 signal range from CO2 max to the ambient and map the first half to increase the zone minimum airflow set point from what it would be without any people in the space up to the zone maximum airflow rate. At this point, the zone would effectively behave as a constant volume reheat zone. The higher half of the CO2 range would be sent up to the air handler controller, where the largest signal from all DCV zones, those are the ones with CO2 sensors, would be mapped to increase the minimum outdoor air set point from the minimum required with no people in DCV zones up to the design outdoor air rate. The reason why we feel this is efficient is because in mild weather, the economizer will be operational, so all zones will be well ventilated. All will be in the lower half of their CO2 ranges. Under this condition, there's little added reheat energy and no added air handler cooling or heating energy. The only time the DCV logic will really come into play is when the air handler is on minimum outdoor air, either because it's very cold or very hot outside. Under these conditions, it is logical that increasing reheat at the zone level will have a smaller energy impact than increasing minimum outdoor air rates at the air handler and overventilating the whole building. Hence, the sequence first tries to ventilate the DCV zones with more supply air, essentially transfer air from overventilated zones, and then calls for additional outdoor air at the air handler. We'll see if ASHRAE's research project corroborates the efficiency of this sequence or finds another to be more effective.
So, it looks like demand-controlled ventilation requirements in the two standards are perfectly compatible. Standard 62 allows it, sometimes Standard 90.1 requires it, and designers can deal with it. Good. Now let's move on to the next area of potential conflict: reheat when dehumidifying. High relative humidity indoors can lead to microbial growth on surfaces, so limiting it reduces the potential for IAQ problems associated with mold, bacteria, and general dampness. Standard 62 includes relative humidity requirements. The key requirement is an analytical limit on zone relative humidity whenever the system is dehumidifying. To comply, designers must analyze the performance of the proposed mechanical system at elevated latent load conditions. With outdoor air at the design dew point condition and with no sensible heat gain due to solar load in the zone, a psychrometric analysis must show that zone relative humidity does not exceed 65%. This analysis evaluates the dehumidification capability of the proposed HVAC system at one particular load condition. Depending upon building design and climate conditions, some systems can meet this requirement without direct humidity control. Other systems can't. Let's look at a few systems analyzed as required by Standard 62. Perhaps most common, the single-zone constant volume system supplies a constant quantity of mixed air to a single zone at a temperature that depends on sensible load. As load changes, the zone thermostat modulates cooling capacity to maintain dry bulb temperature at set point. On the psych chart, outdoor air mixes with return air, and this mixture passes through the coil to be cooled and dehumidified. Then this cold, dry air is delivered to the zone where it offsets sensible heat and absorbs moisture. At full load, zone temperature is controlled to set point, while relative humidity rises to 52%. The cooling coil removes 4.8 total tons from the mixed air, but let's see what happens at the Standard 62 analysis condition. Here's the same system at design dew point, with no solar load in the zone. It's cooler outdoors, so sensible load is lower, but there's more moisture, so the latent load is higher than at design. We start our analysis by assuming a return air condition from the zone to find the mixed air condition. Since lower sensible load requires less cooling capacity, the constant volume system delivers warmer and wetter supply air. The resulting zone humidity is much higher than we initially assumed, so we iterate until the resulting return air condition matches the condition initially assumed. Relative humidity rises to 67%, so this system in this climate doesn't comply with standard 62. Notice that the cooling coil, which was sized for 4.8 tons at full load, uses only 3.7 tons at this load. So the increase in relative humidity at part load is not an issue of the coil being undersized. It's an issue of how the system is controlled. The thermostat reduces coil capacity to match sensible load and at the same time reduces latent capacity. It seems that a lot of designers these days want to decouple the latent load from the sensible load using a dedicated outdoor air unit in a 100% outdoor air system. One air handler dehumidifies all of the outdoor air while local units handle the sensible load in each zone. If the outdoor air delivered to each zone is dry enough, it prevents high zone humidity. An iterative psych chart analysis at the design dew point condition shows that if the outdoor air is delivered to the zones at 52 degrees and the local unit delivers air at about 68 degrees, these two air streams mix in the zone to keep the relative humidity at about 50%. The cold outdoor air offsets part of the sensible cooling load in the zone, while the local unit does the rest. Since the central unit delivers air that's drier than that in the zone, it dehumidifies enough to keep the zone at 50% RH. In this case, this approach complies with standard 62. Finally, let's look at a multiple zone VAV system. It consists of a central air handler or rooftop unit delivering primary air to many VAV terminal units. For each zone, the thermostat modulates primary air volume to match the cooling load in the zone. The central fan, meanwhile, delivers the total quantity of air needed by all zones at a constant temperature that's usually around 55 degrees. An iterative psych chart analysis at design dew point shows that as the sensible cooling load decreases and the VAV boxes reduce primary airflow, the cool, dry primary air limits zone relative humidity to about 57%. So this VAV system example also meets standard 62 without direct humidity control. Clearly, dehumidification depends on system type, configuration, and control. We have analyzed many different systems and presented various publications listed in the bibliography. Here's a comparison of our results for a classroom in a humid climate, like New Orleans, at different load conditions. As we just saw, constant volume single zone systems often don't control RH at design dew point, much less on rainy days. Neither energy recovery nor mixed air bypass configurations control humidity very well. Two-speed fans can meet ASHRAE 62 in this example, and return air bypass works well, and it uses no direct humidity control, so standard 90.1 rules don't apply. Supply air reheat with direct humidistatic control works well too, but here standard 90.1 rules do apply, so be careful. 100% outdoor air systems with a dedicated outdoor air unit can meet the standard 62 RH limitation, provided the dehumidified outdoor air is drier than the air in the zone. Even if the outdoor air is reheated, this approach usually meets standard 90.1 since heat is only added to ventilation air. And finally, most VAV systems deliver dry primary air at all conditions, so they maintain reasonable zone humidity without humidistatic controls. We covered analysis of these and other dehumidifying systems in detail in an earlier broadcast and in an applications manual. In summary, to comply with standard 62.1 requirements for dehumidification, pick the right system and control it right. Mick?
In looking at ASHRAE 90.1, it has limitations on simultaneous heating and cooling. There are two sections that we'll cover today: zone controls and dehumidification. We'll go through the dehumidification section first. Unlike the demand-controlled ventilation requirement in high occupancy zones, which is mandatory, these limitations on simultaneous heating and cooling are prescriptive. That means that if the project is following the prescriptive path, they are required. However, if for some reason they would be required by the prescriptive path, but the design team decides not to follow them, these prescriptive requirements may be traded off by using the energy cost budget method. Where humidistatic controls are installed, Section 6523 requires controls to prevent simultaneous heating and cooling of the same airstream. But there are 6 exceptions. Exception A allows variable air volume, dedicated outdoor air, or 2-speed fan systems to use reheat if the airflow being reheated is first reduced to either 50% of the supply airflow or the minimum ventilation rate required by 62.1. The next 2 exceptions allow reheat if there is an individual cooling unit serving the zone. This could be a rooftop, a split system, or even a blower coil with a cooling coil. Exception B allows a unit 6 2/3 tons and able to unload 50% capacity to use reheat at that point. Exception C allows new energy reheat on small units, those 3 1/3 tons or less. Also accepted are humidity-sensitive applications, including computer rooms, museums, surgical suites, supermarkets, and ice arenas. So these and similar applications can use reheat for humidity control. Using exception E, reheat may be used at any time if 75% of that reheat energy is site recovered or site solar. We've seen many projects use this exception and recover heat, either directly from the refrigerant or from condenser water. For example, on a water-cooled chiller with a heat recovery condenser, it can help satisfy this exception. There's a broadcast and an engineer's newsletter on waterside energy recovery. The final exception is targeted toward active desiccant systems that dry but also heat the airstream. Often these systems require recooling of that hot, dry airstream. As long as 75% of the heat added by the desiccant is removed by a heat exchanger using energy recovery, the system is allowed. As Dennis showed, most VAV systems don't need humidistatic controls. However, if you decide to use supplier temperature reset and have humidistatic controls to ensure proper space humidity levels, you need to either reduce the airflow to 50% or recover the energy used for reheat. I was in Puerto Rico in September of this year discussing humidity control, and heat recovery has been used for years there to minimize energy use. At 25 to 30 cents per kilowatt hour for energy costs, there's a real incentive to recover heat. So Steve, do you see any conflicts between ASHRAE standard 62.1 and 90.1 with respect to dehumidification?
No, I don't. Compliance with both standards is possible with the same system design. Standard 90.1 limits how dehumidification can be done to reduce energy waste, but there are many exceptions to the simultaneous heating and cooling limitation, leaving many options for designers. Compliance is actually very easy. Here are a few compliance options designers should consider. First, what about VAV systems? As Dennis showed, for almost all applications, humidity control is inherent with VAV systems. No special features or controls are required. One caveat though, if supplier temperature reset is used based on zone demand for systems in humid climates, make sure the warmest supplier temperature still provides dehumidification at the coil. The upper supplier temperature limit can be reset based on space or return air relative humidity, or it can be reset by outdoor air temperature to ensure that colder supplier temperatures are maintained when outdoor air humidity is or can be high. Compliance with 90.1 for dedicated outdoor air systems is also easy. You can dehumidify pretty much without limitation since 90.1 allows reheat of the entire design minimum outdoor air rate. However, efficiency can be improved by reheating with heat recovered from the exhaust air stream or, for DX systems, by hot gas from the cooling system. 90.1 also offers many exceptions to allow reheat for humidity control with single-zone systems. First, as Mick showed, small systems are exempted and may use any type of reheat. Again, efficiency can be improved by using hot gas, coil bypass, and sensible heat recovery, but they're not required. For larger systems, variable volume should be considered using either variable speed or two-speed motors. This capability will be a requirement for systems 7.5 tons and larger in 2012. The intent of Addendum 90.1N was to reduce fan energy, but variable volume also improves humidity control. On the next slide, I will show how VAV single-zone systems can be controlled. The rapidly falling cost of electrically commutated motors, or ECMs, which are inherently variable speed, is making it cost-effective to make even the smallest fan coil variable speed. ECMs are also more efficient than standard motors. One last reminder, don't oversize constant volume systems. Not only does this increase fan energy, but it results in poor dehumidification. Another choice, simply don't use constant volume systems. Again, the falling cost of ECMs and variable speed drives makes VAV an option for almost all chilled water and variable capacity systems. This figure shows how variable speed motors can be controlled on single-zone variable volume systems. At full cooling, on the right side of the figure, the fan is at full speed and the supply air temperature set point is at the minimum, such as 55 degrees. As the cooling load goes down, the supply air temperature is kept constant while fan speed is reduced down to a minimum. The minimum speed can be a function of the ventilation requirements or air distribution limitations. For DX systems, the minimum speed is also limited by the refrigeration unloading capability. The system generally stays at the minimum speed through the deadband and into heating with the supply air temperature set point reset to meet zone load requirements. Single-zone VAV systems reduce fan energy and improve humidity control.
Good stuff, Steve. Thanks for covering the dehumidification issues. To make this next section more understandable, we're going to change the order and cover the standard 90.1 requirements with respect to zone controls first. Often section 6251 on zone controls is pointed to, and it's claimed that there's no way to make a VAV system comply with this section. There are limits on simultaneous heating and cooling. This includes not mixing air streams, even if the cool airstream has been made that way through the use of an economizer. Note that reheating or recooling, for instance in a desiccant system, is not banned since there are exceptions based on zone airflow. Let's look at those exceptions. First, prior to using new energy for reheat, reduce the amount of zone airflow that must be reheated. There are 5 possible limits that we'll look at in a minute. Next, the restriction on simultaneous heating and cooling does not apply to zones with special pressurization requirements or code-required minimum circulation rates. Both of these may occur in healthcare facilities. You may do any amount of reheating if at least 75% of the reheat energy is site recovered or site solar. Again, this could be directly from refrigerant in the form of hot gas reheat or from the condenser water of a water-cooled system. Now, let's look at the zone airflow limits allowed. Before reheating or recooling can be performed using new energy, the supply airflow in the zone must be reduced. By definition, a constant volume system cannot meet any of these exceptions, but many variable air volume systems can be designed and operated to comply with one of the airflow limits allowed by this standard. Let's look first at exception A, setting the zone airflow to the required ventilation airflow. Considering the requirements of standard 62.1 on a VAV system, this will require bringing in 100% outdoor air when any zone closes to this minimum. Dennis will cover this in a few minutes. Since this results in high energy usage, exception A isn't used very often on mixed air VAV systems. However, this exception can work very well for dedicated outdoor air systems, since it allows all the ventilation air to be delivered to a zone to be reheated if necessary. There's another exception, that of 0.4 CFM per square foot. Today's energy regulations require better glass, more insulation, and lower lighting power densities than in the past. The bottom line is a reduction in space-sensible cooling load requirements. Since the space airflow required is dependent on this sensible load, if the same supply air temperature is used, the design space airflow is lower than it was in the past. So using 0.4 CFM per square foot as the reheat minimum set point may allow a higher airflow to be reheated using new energy than the next limit. A lot of people seem to gravitate to setting the reheat minimum at 30% of its design airflow. While it's simple, this could cause some issues with respect to heating and stratification. Steve will cover that in a few minutes. It's interesting to note that until the space design airflow reaches 1.33 CFM per square foot, that the 0.4 reheat minimum allows a higher airflow to be reheated. Okay, let's cover the last two exceptions. We don't see the exception for 300 CFM used too often, except perhaps on small zones. And finally, exception E allows us to use the ASHRAE 62.1 multiple zone system equations and set the minimum airflow higher in potentially critical zones as long as the overall system energy usage goes down. We've communicated with other engineers who think this is a tough one to use because it must be approved by the authority having jurisdiction. Later, Steve will share some experiences using this method. So there are a number of ways that a VAV system can comply with this portion of Standard 90.1. Let's bring Dennis back to discuss the requirements of ASHRAE Standard 62.1.
Okay, I think we understand what Standard 90.1 does and doesn't allow for VAV systems. The reheat minimum settings can't be too high, otherwise energy is wasted. But Standard 62 requirements also impact primary airflow to each zone. It must be high enough to ensure proper ventilation at all load conditions. To comply with Standard 62, designers must use the multiple zone system equations, which relate zone outdoor airflow to intake flow at the central air handler. The two standards would conflict if the required Standard 90.1 settings were lower than the Standard 62 minimum outdoor airflow, but that doesn't happen. Of course, that doesn't mean that complying with the two standards is easy. Let's take a closer look. Single-path VAV systems supply variable volume, constant temperature air to all zones. Primary airflow must drop as zone cooling load drops, but this air provides both cooling and ventilation, so it can only drop so far. Once primary airflow reaches some minimum value, any further reduction in zone cooling load results in subcooling. The only way to avoid subcooling is to add heat. So many perimeter VAV zones use reheat at the VAV box. In these zones, designers must determine the right minimum settings to maintain proper ventilation without using excessive reheat. But what's right? That's what we want to find out. But first, let's look at what Standard 62 requires. Three sections apply. Section 5.4 requires that the system receive no less than the minimum required outdoor airflow at any load condition. Since mixing box pressure at the air handler changes as supply airflow changes, VAV systems should use an outdoor airflow sensor and modulating outdoor and return air dampers to comply with this requirement. Section 622 prescribes minimum breathing zone outdoor airflow rates for a long list of occupancy categories and a procedure to determine minimum zone outdoor airflow, especially at design. Section 625, along with Appendix A, prescribes equations to be used to find the intake airflow for any multiple zone recirculating system. These equations must be followed for design, but they also apply at part load. Remember, intake airflow must be sufficient for current ventilation needs at all load conditions. Zone outdoor airflow calculations are straightforward. We covered them earlier. These zone calculations are used to find how much outdoor air must be supplied to each zone, both in the breathing zone and at the diffusers. But for multiple zone systems, 4 more calculation steps are needed to find out how much outdoor air to introduce at the intake damper. I mentioned these equations earlier when I talked about ventilation reset control, but here I'll go through the calculations in more detail. Like the first 3 steps, the 4th step applies to each zone. Find the fraction of outdoor air needed in the discharge airstream. For design purposes, use the minimum expected discharge airflow at the condition being analyzed. This minimum may or may not equal the reheat minimum setting for the VAV box. More about this in a minute. The 5th step is to find the uncorrected amount of outdoor air needed in all breathing zones. Similar to using load diversity in VAV systems, designers can take credit for occupant diversity when finding this airflow. Occupant diversity is the ratio of actual population to sum of peak zone populations. I always say that this ratio allows you to ventilate for the actual number of occupants in the system rather than for the number of chairs. Incidentally, by using this credit, some multiple zone systems might actually need less total intake airflow than, say, a bunch of single zone unit ventilators or a 100% outdoor air system applied to the same zones. The 6th step is to find the system ventilation efficiency. To do this, first find the average outdoor air fraction for the system. It's the ratio of uncorrected outdoor airflow to the highest expected system airflow at the condition being analyzed, which is probably block airflow for conservative designers. Next, find the ventilation efficiency for each zone, and then the system ventilation efficiency, which is simply the lowest of all the zone efficiencies. The 7th step is to divide the uncorrected outdoor airflow by the system ventilation efficiency to find outdoor air intake flow required. That was pretty quick, but if you want more details about ventilation calculations, we did a broadcast and wrote some newsletters and some journal articles about it, so the bibliography includes plenty of resources. Okay, for most designers, the hard part is the 4th step, because you need to know the minimum expected primary airflow for each zone at the condition analyzed. What is it? Is it the minimum zone outdoor airflow needed to comply with Standard 62? Or is it the reheat minimum setting established by Standard 90.1? Or is it some other value? Here's a plot of discharge airflow versus load for a typical VAV zone. As zone cooling load decreases from design, discharge airflow drops until it reaches the cooling minimum setting established by the designer. This setting might be based on sensor or diffuser performance or some other rationale. It can be any value as long as it's not less than the minimum outdoor airflow required by Standard 62. As zone load continues to drop below the deadband, reheat typically kicks in, and discharge airflow pops up to the reheat minimum setting. This setting must be equal to or less than the value established by Standard 90.1. But again, it can be no less than the minimum outdoor airflow. There are other ways to control reheat, of course, but here we simply assumed constant airflow and variable temperature during reheat. When solving the multiple zone system equations to find the intake airflow required, designers must not only find the outdoor air needed in each zone, but also establish the minimum expected discharge airflow. This value must be equal to or greater than the minimum airflow setting at the condition being analyzed. For instance, when analyzing intake requirements during cooling, the minimum expected airflow can't be less than the cooling minimum setting. But what values should be used for these settings? Some designers might want to set both the cooling and reheat minimums equal to the zone outdoor airflow and use this value as the minimum expected discharge airflow as well. But that would be a mistake because it would result in an outdoor air fraction of 1, which would require 100% outdoor air. Conservative designers might use the Standard 90.1 reheat minimum for both the cooling and reheat minimum settings. Then they assume that the critical zone is reheating when all other zones are cooling, so they use this same value as the minimum expected discharge airflow for design purposes. The required intake airflow will be less than 100%, but the actual value depends on the difference between standard 90.1 and standard 62 requirements. I actually prefer this method because it's easy to figure out, but it can result in relatively high intake airflow in some cases. If the reheat minimum setting allowed by standard 90.1 is too close to the minimum outdoor air required by standard 62, the outdoor air fraction may be close to 1. This probably doesn't happen in office buildings, but it can happen in schools. Designers who don't want to be as conservative might use a building performance analysis to determine the highest outdoor air intake flow at any load. Then use the discharge airflow at each zone at this hour as the minimum expected value at the condition analyzed. Since this expected value is probably greater than the reheat minimum, this approach reduces intake airflow compared with the previous approach. Some designers use Trace 700 to help with this analysis and to help determine minimum settings that lower annual energy use and satisfy standard 90.1. Other designers use a spreadsheet, like the one that comes with the 62.1 user's manual, to do a series of what-if calculations in order to find reasonable values for minimum settings and intake airflow. Steve will talk about this approach in a moment. Whatever approach is used, the requirements in the two standards don't conflict, but that doesn't mean it's always easy to comply. In some cases, it might be necessary to adjust system configuration. For example, standard 62 might require a very high outdoor airflow for an interior conference room. Although standard 90.1 allows designers to raise the reheat minimum setting to equal it, this forces 100% outdoor air at the intake. For zones like this, designers might use a series fan-powered box to raise the minimum expected airflow without actually raising the minimum settings. Of course, if designers can use 75% site recovered or solar energy for reheat, the system is exempt from standard 90.1 limitations, so minimum airflow settings in all zones can be as high as the designer chooses. Now, let's find out about a designer's view of reheat minimums. Steve?
Well, once again, we ask, are there conflicts between the requirements of 62.1 and 90.1 with respect to simultaneous heating and cooling? And once again, strictly speaking, there are no conflicts. It is possible to design a mechanical system that meets both standards. However, it is more difficult than the previous two potential conflicts we have discussed. Some common VAV systems will not be able to meet both 62.1 ventilation requirements and 90.1 zone reheat limitations without very high outdoor air rates. In particular, for most buildings except in mild climates, traditional single duct VAV reheat systems will not work without a very high minimum outdoor air rate. It should be noted that 90.1 does not place a limit on minimum outdoor air rates, so technically almost any VAV system can be made to work. Simply supply 100% outdoor air. But that will have a first cost and energy cost impact that most designers and owners will not accept. But VAV is still an option. We will see some variations on VAV system design that can meet both standards in an efficient manner. It seems many people have become convinced that VAV is dead and dedicated outdoor air systems are needed to meet these two standards. That is not the case. VAV can work, and moreover, it can also be more efficient than dedicated outside air systems, particularly in mild climates. One tool designers should use to help meet 90.1 and 62.1 efficiently is the multiple spaces spreadsheet provided with the 62.1 user's manual. We use it on our VAV projects and find it to be a powerful tool. The spreadsheet, called 62 MZ Calc, allows designers to experiment with different design and operating scenarios on their system so that both reheat and minimum outdoor air rates can be minimized. One of the keys to using the spreadsheet effectively is to be realistic. Standard 62.1 does not require your system to handle any combinations of variables that might occur, just those that can reasonably be expected to occur under normal operation. For example, take an interior conference room. A conservative engineer might assume that the space is fully occupied and yet the VAV box serving the space is at its minimum set point. But that's not realistic. A more realistic but still conservative scenario is that everyone is present, the lights are on, but there are no plug loads such as an LCD projector or a PC you designed for. Assume they're off. A simple load calculation can be used to determine the resulting airflow rate. That rate, not the zone minimum, should be used in the spreadsheet. Another practical tip, include occupant diversity. The sum of the number of people in each zone will typically far exceed the number of people simultaneously expected to be served by the system. Taking advantage of diversity can completely offset the inefficiency of multiple space systems. In other words, a dedicated outside air system sized for the sum of each zone peak outdoor airflow rate will typically have about the same outdoor airflow rate as a VAV system if occupant diversity is taken into account. Another tip, use transfer air on potentially critical zones. In other words, rather than raise the design or minimum airflow set points to spaces that are driving the system ventilation rate, use air transferred from other spaces or from the return system. Examples include fan-powered mixing boxes and dual fan, dual duct systems. Transfer air can reduce the system outdoor air rate by taking advantage of unused outside air from other spaces, and it also can improve zone ventilation effectiveness in the heating mode by reducing supply air temperature and maintaining diffuser throw. It also can reduce or even eliminate zone level reheat. I'll show you an example of that in a minute. This is a screenshot of the 62 MZ Calc spreadsheet using the example system described in the Standard 62 User's Manual. It may be difficult to read, so please refer to your handout. The spreadsheet has a directions tab that explains in detail how it is used. We don't have time here to cover everything, but let me highlight a few key features. The spreadsheet has 4 main input sections in addition to the project info section at the top. First, there's a section on air handling system information. All these cells are populated automatically by the spreadsheet from the zone information listed below, but you can overwrite any of the cells if need be. All of the cells must be overwritten if you choose not to enter all of the zone data below, but more on that in a minute. If all zones are entered in the spreadsheet, you still will likely overwrite cell I9 for VAV systems, since the sum of zone airflow rates generally exceeds the design fan airflow rate due to diversity. Diversity also applies to occupants. In this case, the actual number of people expected in the area served by the system is half of the sum of the people in each zone. This level of diversity is not uncommon, since at the zone level, every conference room is assumed to be fully occupied, each private office has 2 occupants, the lobby's full of people, etc. It is not likely that all these spaces will be at the peak occupancy concurrently. Next is the zone input section. It is only necessary to enter the potentially critical zones, since the critical zone will determine the ventilation rate regardless of operating conditions at other zones. But it is usually simpler to enter every zone. That way the spreadsheet will automatically sum up system information, and I don't have to make a judgment call about which zones are maybe critical. The next section is where the user describes the system at the operating conditions being analyzed. This section allows many different conditions to be analyzed without overwriting the basic system design data in the previous section. The final section of the spreadsheet is the results section. The ventilation efficiency is listed along with the required outdoor air rate expressed in terms of CFM, CFM per square foot, CFM per person, and percent of design supply air rate. Standard 62 does not say what conditions to analyze, and of course with VAV systems, there are an infinite number. But the user's manual suggests looking at 2 conditions, the design cooling condition and the design heating condition. Peak cooling can be the critical condition because the primary supply air has the smallest percentage of outdoor air of any operating condition. But for many VAV systems, the heating condition is the most critical, since primary airflow rates to spaces are generally at their lowest. This screenshot shows the design cooling condition. The critical zone in this case, highlighted by the spreadsheet in purple, is an interior conference room. This zone can be made to be non-critical by installing a series fan-powered mixing box with the supply air rate a bit above the design primary cooling rate. The next most critical zone in this case, the 2 north conference rooms, would then determine the design outdoor air rate. Now let's look at the heating conditions. First, we'll assume the system is a standard VAV reheat system with 30% minimum set points on the exterior zones. We will assume the interior zones are cooling, but at 75% of their peak, as might occur on a cold morning. On row 23, we enter 30% for the exterior zones and 75% for the interior zones. The spreadsheet automatically determines the primary fan system will be at 46% in cell I-23. On row 24, we enter the code for overhead heating system whose supply air temperature exceeds the space temperature by 15 degrees, which is typical of most reheat systems. The zone air distribution effectiveness drops to 80%. The critical zones are now the two north conference rooms. But look at the results section. The ventilation efficiency and the rates are all undefined. That means that no matter what amount of outdoor air we bring in, these spaces will not meet Standard 62. In this case, we use 30% minimums, but Standard 90.1 has other exceptions that allow higher minimums in some cases. For instance, Standard 90.1 also allows minimum set points to be equal to 0.4 CFM per square foot. In this analysis, the minimums were set to the larger of 30% and 0.4 CFM per square foot. This is easily done with a formula in the spreadsheet. The minimums to the north conference room increase to about 40%, and the critical zone switches to a corner conference room. The results section shows that this scenario is possible, but only if the system outdoor air rate increased to 3524 CFM, more than double the 1565 CFM required for the cooling scenario. We'd like to keep the outdoor rate lower and also would like to reduce reheat. While the reheat minimums in this scenario meet 90.1, they still will result in high energy usage. So let's try putting series fan-powered mixing boxes in each of the exterior conference rooms. On line 20, we use the pull-down menu to model Induction Terminal Unit, ITU. The spreadsheet enables line 21, which is the entry for E sub R, a measure of how well return air quality represents that of the overall average system return air. ASHRAE recently finished a research project on E sub R and found that it varied, as expected, depending on the location of the box inlet relative to the space served by the terminal. Typical design values will vary from 0.5 to 1. Refer to the ASHRAE Research Project 1276 for details. In this case, we have assumed that E sub R is 75%. We also changed the percent of design airflow rate on line 23 to 100%, since these are series fan-powered boxes. And we changed the ventilation effectiveness code to that corresponding to overhead heating with air less than 15 degrees above the space, which is possible with fan-powered mixing boxes. The critical zones are now the two north conference rooms again, but the system outdoor air rate drops by more than half to 1690 CFM, about the same as that required in the cooling mode. In the previous slide, we saw how use of fan-powered boxes in critical zones can reduce design outdoor air rates by 50% compared to VAV reheat systems. But what happens if we use fan-powered boxes in all other zones? The answer is almost nothing with respect to outdoor air rates. The critical zones dominate in that regard. But fan-powered boxes can nevertheless be beneficial in non-critical zones. They can allow the primary air minimums to be low or even zero, virtually eliminating reheat losses and reducing primary fan energy. Of course, there's a price. Fan-powered boxes cost more, make more noise, and their fan energy, even with ECMs, can be significant, potentially offsetting the savings from low minimums. So they may or may not be cost-effective. So, once again, we see that there is no conflict between Standard 62.1 and 90.1 with respect to VAV systems. But meeting the two standards can result in high outdoor air rates without clever design. Remember these tips. First, be realistic in your operating scenarios when calculating outdoor air rates. Second, use transfer air in critical zones. This will reduce outdoor air rates and reduce reheat energy.
Thanks, Steve. That brings us to the question and answer portion of our broadcast. So let's get started. Steve, the first one's going to be for you. And it is, I have designed a couple of office buildings using the ASHRAE Standard 62.1 outdoor air calculations. In my calculations, I found that a storage room always seems to dictate the outside air requirements for the entire system. In my opinion, this can't be the intent of the standard. Please provide a description of why this happens to be the case and how we can still meet the intent of the standard without storage rooms being the driving factor in our designs.
Well, it certainly wasn't the intent for a storage room to drive the ventilation rate. There are probably two factors here. One is that the ventilation rate in a storage room is driven by the square footage, and the load in the space is very low, so the two can be very close, which might cause it to drive the outdoor air rate. A couple of things to consider. One is that storage rooms are not always occupiable spaces. You need to look at the definition of occupiable space. If it's not frequently occupied by people, then it actually doesn't count as an occupiable space, and no ventilation is required by Standard 62. If it is required, then there are ways to fix that zone, like we discussed before, by using transfer air to increase the amount of ventilation into the space indirectly rather than using primary air.
Thanks, Steve. Mick, the next one's for you, and it is, was demand control ventilation required prior to the 2007 release of ASHRAE 90.1?
Actually, it was. In 1999, there was a demand-controlled ventilation section in the standard. It had different limits or different thresholds before demand-controlled ventilation became a requirement. It was a different square foot per person and a different airflow and perhaps a square foot limit. So it was in the 1999 version. It's more stringent in the 2004 and 2007 versions.
Thanks, Mick. Dennis, the next one is for you, and it is, looks like the focus of the standard 62.1 is CO2 concentration. Are there any limits which are placed on mold concentration?
Well, okay. This gives me an opportunity to say an important thing, and that is that none of there are no contaminants identified in the standard with the contaminant concentration limitation, including CO2. There's certainly nothing for mold concentration. The ventilation rate procedure of the standard, which is what we've been talking about, focuses on bringing in a prescribed amount of outdoor air, the intent of which is to dilute contaminants, but we never put a limit on or a target concentration on any contaminant, whether it's CO2 or mold spores or any other contaminant.
Thanks, Dennis. Mick, the next one I'm going to start with you. Can you comment on using DCV strategy to gain points under LEED credit EA1, optimize energy performance, versus IEQ credit 2, increased ventilation?
Okay, and I'll probably put this over to Dennis afterwards. EA Credit 1, you can get move toward credit points in EA Credit 1 Optimize Energy if demand control isn't required per standard 90.1 already. So if you meet the threshold limits, then it has to be in the baseline building that's modeled for the EA Credit 1. If it's not in the baseline building, or if it's not required by the standard because you have different limits, then you can put demand-controlled ventilation in your proposed design building. The baseline building does not have it, so you can move toward reducing the energy cost and toward energy and atmosphere credit number 1 points. Dennis, you probably want to address the 62 part.
Well, what I want to say is about EQ credit number 2. Which says you have to increase the outdoor airflow, that is the ventilation airflow, by 30% over the minimum requirement in Standard 62. So you can get this credit 2 whether you do any demand control ventilation or not, just by increasing the outdoor airflow. By the way, if you use CO2-based demand control ventilation in a zone with 30% more outdoor air, obviously your high limit setting for CO2 concentration would be different because you have a different outdoor airflow. Steve, were you going to tell us something a little bit about?
Yeah, I wanted to add to that, Dennis. Many people think that complying with EQ Credit 2, where you raise the ventilation rate by 30%, will hurt you in the energy credit, EA Credit 1. In fact, it's usually the opposite. The standard 90 doesn't have a limit on outdoor air rate. So when you increase the ventilation rate for your proposed design, the baseline design ventilation rate also goes up. And because most of the time, your plant, your heating and cooling plant will be more efficient than the baseline heating and cooling plant, you'll actually improve, because the load goes up, you're actually going to improve your relative energy performance to the baseline. So it's not uncommon for you to get the credit EA by increasing ventilation rates 30% and actually get more credits for EA Credit 1.
Great, thanks guys. Steve, the last question I'm going to give to you, and it is, does the proposed strategy presented by Steve on the multiple zone system CO2 slide violate the ASHRAE 90.1 requirements limiting maximum simultaneous heat-cool airflow?
That's a good question. We do show that the reheat goes up to 100% for the zone before outdoor air is increased at the system level. And that's okay because Section 652 has an exception, E5, that says that you can have any amount of reheat provided the overall energy use of the system is lower. And of course, in this case, the whole reason for doing DCV is to lower our ventilation rates. So we don't know quite yet if that strategy is the optimum, but we're very convinced that it will actually reduce overall energy costs, even though you are reheating at the zone level.
That is about all the time we have for questions today. If we didn't get to your question on the air, we'll answer it offline. Today, we looked at 3 areas of Standard 62.1 and 90.1 in which designers believe conflict exists. Mick, would you summarize the takeaways for our viewers?
Sure, Jeannie. First, demand-controlled ventilation. It's allowed by 62.1 and in some high occupancy areas required by 90.1. There's no conflict. Steve pointed out that monitoring carbon dioxide levels is the prevalent way to implement DCV and walked us through how the sensor outputs can be used to vary outdoor airflow. In addition, he mentioned that ASHRAE is developing research to compare various strategies for incorporating DCV in multiple zone systems. Next, we examine the dehumidification requirements in each standard. 62.1 requires that humidity levels be maintained below 65% relative humidity when it's cooler but more humid outdoors. When humidistatic controls are employed, 90.1 allows systems to use reheat for dehumidification through use of 6 possible exceptions. Steve discussed the advantages of variable airflow to maintain humidity levels and pointed out that even when energy recovery is not required, it can be a good idea. Finally, we looked at zone reheat for temperature control and saw that 90.1 requires the zone airflow to be reduced prior to using new energy for reheat. This can be a challenge since Standard 62.1 requires minimum ventilation in the breathing zone. Steve pointed out that while there are no conflicts, the solution is to properly select, design, and operate the system. He reminded us to be realistic when calculating outdoor air rates and to use transfer air in critical areas to reduce the amount of outdoor air required. Fan-powered boxes can really help us here. Jeannie, how about sharing some of the information available in the references on 62.1 and 90.1?
Sure, Mick. There are a number of publications available that provide more information on the topic today. Dennis has recently published an Engineers Newsletter addressing this topic, and a bibliography detailing these and additional resources is available from your local site coordinator. Past broadcasts are available on tape or DVD, depending on the vintage. So please check out the website for more information on specific broadcasts. And we thank you in advance for filling out an evaluation form before you leave. Now, based on feedback from these forms, we are excited to announce the dates and topics for our 2009 Engineers Newsletter live season. In March, we'll provide an update on the USGBC's LEAD 2009 documents. We'll cover changes in the number of credits available, distribution of those credits, and new capabilities available in modeling tools used to achieve optimized energy credit. In May, we'll design a small ice storage system from layout to operation and control to demonstrate how to make it affordable on small chilled water systems, and we'll address the most common stumbling blocks. And in November, we'll discuss complex air handler configurations and the controls needed to operate them in the context of system strategies. So mark your calendars. And we can't sign off without thanking Steve Taylor from Taylor Engineering for his time preparing for this broadcast and for being here today. Thanks for joining us, and we look forward to seeing you in spring.